So, in this lecture sessions under management of quality, I will be discussing 7 tools of TQM and new 7 tools. As you are aware that use of tools and techniques for quality control and improvement purpose is a must. Now, and whether you are trying to implement say the quality management systems in an organization as a whole, or at a particular the location, at the shop floor, at a particular sections of the department. Now, any exercise on quality is essentially an exercise on variability, and for carrying out such an exercise on variability, what you need data collection, and from the data you collect, or the set of data you collect, first thing what you have to do, that means by analyzing the data, we need to get some relevant information related to quality. As such, data, unless the data are analyzed, how do you get the meaningful informations from the data? So, at the first stage, what you do, you use those the tools and techniques which will help you in presenting the data, as well as to draw some meaningful conclusions out of this data, or meaningful information out of this data. This is point number 1. Point number 2 is, in many cases we opt for at the initial stage a graphical method of data presentations, because if the graphical method you use, the data will be the visible, and the information which you get out of this data, that also you can interpret very easily, comparatively easily. So, this is one advantage. And so, at the first instance, what you do, that you collect data, and these data are to be presented in a certain styles, and so when you and these data are to be looked into, and you need to know the information from several perspectives. So, what we try to do, we look at the methods for describing data sets graphically, because it will be understood very easily by all the concerned people. That is the basic assumption. These methods help us learn about the characteristics of a process, to its operating state of affairs, and the kind of output we may expect from it. Is it okay? So, this is all we are referring to the meaningful information about the process behavior, about the product performance, etc., etc. Because graphical methods are easy to understand and provide comprehensive information, they are a valuable tool for the analysis of product and process data. This we are always referring to. The information they provide on existing product or the process characteristics, mostly related to the quality, helps us determine whether these characteristics are close to the desired norms. Is it okay? Several of the graphical techniques help us identify where to focus quality improvement efforts. Is it okay? So, as soon as you get the meaningful information, then you can interpret this information, and whether it is acceptable to you or not, whether the condition as known or as understood, whether it is acceptable or not. So, that is very vital, the knowledge you have. Such tools are beneficial to any company regardless of its current level of quality achievement. Now, at the first instance, we will refer to certain tools used in TQM framework. So, there are 7 such tools you come across. So what are these 7 tools of TQM? Frequency distribution and histograms. Maybe many of you are aware of how to draw the frequency distribution and histograms, and the check sheets, the next one, Pareto charts and the diagrams, named after Italian economist Alfredo Pareto. Fishbone diagrams or the Ishikawa diagrams, or they are also referred to as the cause and effect diagrams, the run charts, the scatter diagrams or the scatter plots, and the control charts. So these are the 7 the tools of TQM. And so what is frequency distribution of the histograms? A frequency distribution is a rearrangement of the rare data in ascending or descending order of magnitude. Is it okay? Such that the quality characteristic is subdivided into classes. So there will be class intervals, so number of class intervals, and the number of occurrences of each class is presented. Now I will show you a table, and this table shows the inside diameter. There is an example in millimeters of metal slips produced in a machine shop for 100 randomly selected parts. So this is the problem. So 100 data points you have collected. 20 samples, each of size 5, were taken. Simply looking at the data in table 1 provides little insight about the process. Okay. So that means this is just a raw data in the table, in a table. So you may not, by looking at this raw data, you may not be able to, to draw any meaningful, say, conclusions. Using the data in table 1, we can construct a frequency distribution like the one shown in table 2. So first I will show you the table 1, and then we will move to table 2. When there are outliers, the values that are too large or too small compared to the majority of the observations. I repeat, that means always there will be outliers. When you start collecting the data, due to some reasons, you will find that some of the data points may be very, very small or very large compared to the majority of the data points. So they may be referred to as the outliers. Is it okay? And obviously it is your objective that you try to identify these outliers. You have to define them, and you have to remove the outliers, and you also must know what are the causes of getting these outliers from a system. Is it okay? So what do you do? So inside diameter of the metal slips. How many data points you have collected? This is the 20 in each sample. How many samples you have? Like say 1, 2, 3, 4, 5. So altogether you have 100 data points. Is it okay? And it's a variable. So the general notation is observation is X, 5 per sample. Okay. So this is your, this data you have collected. Looking at this data, you cannot get any say meaningful information. So what you do? You have to first you try to construct the frequency distribution. So you have, here 49.89 is the minimum value, and 50.11 is basically the maximum value. Is it okay? So this is the range. Now how many the class intervals you will have? So normally there is a formula. That means if suppose you deal with n number of data points, is it okay? So the root over n, is it okay, could be the number of class intervals. Is it okay? So if it is 100 data points, that means you try to have root over 100, that means the 10 class intervals, you arrange them. And while you define a class interval, make sure that the width in each class interval must be same. Is it okay? So this is one approach. Okay. So this rule is followed, and you have all these class intervals. Like say first one is 49.89 less than equals to x less than equals to 49.91, and in the next one 49.91 less than equals to x less than equals to 49.93. So this way you proceed. Ultimately you get the last the class interval, 50.09 less than equals to x less than equals to 50.11. Is it okay? So, these are the tally marks we have. That means now you refer to the data set and you check how many data points you have within this interval, this interval, this interval and so on. So, this is referred to as the frequency. You have 100 data points, so this is the distribution, right? And then the relative frequency means the total number divided by 100. So, here is 100 by 100, so 1.0, and you just each one is divided by 100. So, cumulative frequency is 0.0, say 1, 4, 10, you add them, 1, then 4, then 10, then 21 like this. So, ultimately cumulative frequency will be 100 and cumulative relative frequency is 1. So, this is very simple. So, a histogram is a graphical display of data such that the characteristic is subdivided into classes or the cells. So, these have already determined. So, these are the steps involved. The following steps are used to construct a frequency diagram. Okay, so find the range, then choose the number of classes or the cells. You use this formula root over n, determine the width of the classes, determine the class boundaries, is it okay, and draw the frequency histogram. Okay. So, for the data in table 1, now you have this one, class boundaries are this one, already we have determined. The midpoint you say the 49.89, 49.91, midpoint is 49.90, frequency already we know, and the cumulative frequency already you know. Is it okay? So, the range is 50.10 minus 49, so 0.2. So, 0.2 is divided by 10, that is 0.02. Is it okay? So, just go through this one. So, the histogram, now you draw this one, histogram. So, frequency histogram of the sleeve diameters. Is it okay? Same thing you do. And now, you the plot the cumulative frequency versus the class interval, so the midpoint in each class. Is it okay? So, you get this is the cumulative frequency histograms. Is it okay? All right. So, this is cumulative adding and ultimately you become 100 over here. Is it okay? So, this is cumulative frequency histogram. So, from frequency histogram you will come to know that what is the range of the variation, that is one important aspect, and another one you will get an idea about the distribution. Is it okay? Whether you may assume it to be symmetric or asymmetric, or the skewed to the left, the skewed to the right. So, all sorts of say the information you may have when you study this histogram. Is it okay? Right. So, next one is the check sheets. The fuel that powers the total quality tools is data. Is it clear? This is the statement we make. But unless and until you start collecting data, there cannot be any exercise on quality. That is the basic assumptions we make. In many companies, elaborate systems of people, machines and procedures exist for the sole purpose of collecting data. Is it okay? Many companies are literally drowning in their own data, while at the same time not knowing what is actually going on. They are data rich and information poor. Is it okay? So, information you must be able to draw from the data. Otherwise, this entire volume of data may be referred to as a simple junk. The check sheet can be a valuable tool in a wide variety of applications. Its utility is restricted only by the imagination of the person seeking information. The check sheet can take any form. The only rules that the data collection can be the equivalent of entering a check mark, and that the displayed data be easily translated into useful information. So, the check sheet is used, applied to any work environment, not so the check is widely used, not only just you can apply only to the factory floor, at the factory floor. The purpose of check sheet is to make it easy to collect data for specific purposes. For example, suppose we are manufacturing parts that have a specified dimensional tolerance of 1.120 inch to 1.130 inch. During the week, each part is measured and the data is recorded. Table 4 is a summary of the week's results. So, this way you just get the data. So date, and this is the date, the length, and the length. Is it okay? So different dates, different data. So this is weekly summary of shaft dimension tolerance. This is not a check sheet. Is it okay? So you just collected the data. Then what do? You create such a check sheet. That means how many the points you have within this. Is it okay? So entry data of month for data point. So this is just another way for presenting the frequencies in a different ways. That means against a particular length, against a particular dimensions, like on the 13th day this has occurred, 11th day this has occurred, this has occurred on 11th, 12th, 13th, 14th. That means this is the number of occurrences will be more in almost all the days. Is it okay? So this way you just present the check sheet. So a simple check sheet this is a simple check sheet in the figure 3 are entered more easily, and once entered provide a graphical plan of the performance. To set up a check sheet, you must think about your objective. So this is, in these examples, we are making shafts to a specifications. We wanted to know how well the machine was performing, a graphical warning whether the machine started to deviate, and information about defects. So this is a general, the information you get out of this check sheet. Next one is the Pareto diagram. Now the Pareto diagram is named after Alfredo Pareto, an Italian economist in the 1848-1923 era. He found that the wealth is concentrated in a few people, and he proved for the first time with the data. This observation led him to formulate the Pareto principle, that the majority of the wealth is held by a disproportionately small segment of the population. So this was his conclusion, and I think you can draw these conclusions even today for any nation, whatever may be the reasons. Joseph Juran realized that this principle applies to quality improvement as well. So in manufacturing or service organization, for example, problem areas or defect types follow a similar distribution. Of all the problems that occur, only a few are quite frequent, the others seldom occur. Is it okay? There could be many reasons for deviation. What you will find, that the majority of the cases, is it okay? The problem occurs due to only few causes. Is it okay? So that we should get an idea. So you have to draw the Pareto diagram. Thus, in grouping these problem areas into two categories, they are labeled as vital few and the trivial many. That means there could be many causes contributing to the problem, and when you list down all these causes, you will find there are some, the non-trivial, very few. They are contributing to the problem most of the time. Whereas the many causes, they are trivial many. They may not be contributing to the causes to that extent or quite significantly. So the Pareto principle also lends support to the 80-20 rule. This is referred to as 80-20 rule, which states that 80% of the problems, non-conformities or defects, are created by 20% of the causes. Okay, this is just a general observations. In some cases, 90% of the problems may be created by say 5% of the causes, but initially when they started analyzing the data, they used to have these sort of conclusions. That's why sometimes we refer to 80-20 rules. Okay, so Pareto diagrams help management quickly identify the critical areas. So so you need to identify the non-trivial, the few causes initially, and if you can remove these causes from the system, obviously, the majority of the problems or the systems will become almost problem free. Okay, so these are the steps. So you just go through all these steps. Is it okay? This is very clearly understood, like the step 1, steps 2, step 3, step 4, step 5. Please go through them and decide on the data, like say and the last stage, plot a bar graph. Okay, so like say bar chart you create, and the cumulative frequency you have to compute, and that in the previous case when you go for frequency distribution plotting, histogram plotting, so what is the cumulative frequency. So these are the 5 steps you create. Here is an example. Okay, so let me go through these examples. All the steps will be made very, very clear. So the data are gathered regarding the types of non-conformance in a textile mill. Table 5 lists the problem areas along with the percentage of occurrence of each and the associated annual cost. So, you go through study, you have studied the systems, and what are the the types of non-conformities in a textile mill. So these are problem type. They are coded as A, B, C, D, E, F, G. That means there are 7 problem types. So percentage of occurrence is also given. Then the corresponding cost in US dollars, that is also given, and cumulative percentage of occurrence, that is also given. Okay, so now you have to draw the Pareto diagram. So a Pareto diagram is constructed. These are the problem types. These are the problem types, and this is basically the percentage of total. That means this is basically the frequency of occurrence. So you plot them, and you get this sort of diagram. And when you have the cumulative frequency, you have this one. Is it okay? That means considering all the problems types, you get 100%. So the 40% of the cases, the cause is A. In the around 20% of the problems are due to cause B. So 40 plus 20 plus this one maybe is 12% or 13%. So that exact value will come to know. So first 3 causes contributing to maybe say 40 plus 60 maybe 75% of the total. Is it okay? So first 3 causes becoming very, very critical, and you have to think of ways and means to remove these 3 causes. Is it okay? So this is the basic idea. And cause and effect diagram. So for improving the quality, what you need to do, that means you need to assess the present system. And supposing a system is failing regularly, your machine is failing regularly, and obviously it is a quality related problem. So I must know what are the possible causes, and in a cause and effect diagram, what you try to do, these causes are systematically identified and link it to the cause. Is it okay? So that means the causes lead to a situation. So the causes must be identified, and they should be linked to the particular condition, unfavorable condition, undesirable condition. Sometimes they are referred to as a problem or a state of the system not acceptable to you. Is it okay? Cause and effect diagrams were developed by Kairo Ishikawa in 1943, and that's why sometimes this is referred to as Ishikawa diagram, and those are often called Ishikawa diagrams. They are also known as fishbone diagram because of their appearance in the plotted form. Cause and effect diagrams are used to identify and systematically list the different causes that can be attributed to a problem or an effect. Is it okay? A cause like say failure may be considered as a problem or as an effect. Is it okay? A cause and effect diagram can aid in identifying the reasons or the causes why a process goes out of control. Now, there are 3 applications of cause and effect diagram. First one is the cause enumeration. Second one is the dispersion analysis. And dispersion analysis is very, very vital, because through dispersion analysis you will come to know the effect of variability of in the causes on the variability in the effect or in the problem. So, the dispersion analysis, and of course, you can use it for the process analysis. So, there are three applications. So, here the causes are identified and they are this cause and effect diagram is plotted or created. So, the cause enumeration facilitates the identification of root causes because all conceivable causes are listed. So, that is why it's a group effort is a must, and you take certain time, to identify the causes in a systematic manner. That means a thorough understanding of the system behavior is a must. Is it all right? So, this is an example, and one of the quality characteristics of interest in automobile tires is the bore size, which should be within certain specifications. In a cause and effect diagram, the final bore size is the effect. Some of the main causes that influence the bore size are the incoming material, mixing process, tubing operation, splicing, press operation, operator and measuring equipment. So, these are the possible causes identified. For each main cause, sub causes are identified and listed. Figure 5 shows the complete cause and effect diagram. So, this is the diagram. Is it okay? So, this is the bore size of tires. This is the effect. There are so many causes. They are classed into so many groups. Like, so the operator is one group, mixing, incoming material, measuring equipment, press, splicing, tubing. Is it okay? And against each cause, there are sub causes. Like against cause of measuring equipment, you have could be the reproducibility could be a reason, readability could be a reason, calibration could be a reason, error detection could be a reason. Similarly, for other main causes. Is it okay? So, this is the typical format, and the dispersion analysis, what we do, that means for each cause you collect data and you calculate their variability. That means variability is measured, the dispersion is measured with standard deviation. So, here what we do, this dispersion analysis, that means widths of the reel. So, what is sigma value, that means standard deviation, and for each one you must collect data and you calculate their dispersions. Is it okay? Dispersions, that means the standard deviation you calculate normally, that is the norm. So, so this way you calculate, that just one portion is shown. So, same thing you repeat or you do, okay, for the other main causes, like for the people, what are the sub causes, and you have to collect data, and against each sub cause, what is the value of the standard deviation, is it okay, or the variance, and then you relate all these individual variances with the effect variation. So, the process analysis you do, that means looking at the aluminum casting produced for gearboxes. Suppose this is the process, what you try to do, this is the process stages, is it okay, like say production of molten metal, casting, boring and all. Now, this the stage is affecting to the next stage. That means there are inputs, and these inputs converted into the outputs, and the outputs goes to the casting plus the individual inputs you have. So, this way each stage is presented, what are the causes, okay. So, the sub processes, and against each of the sub processes, what are the factors controlling the process performance, is it okay, at each stage. So, when you draw the cause and effect diagram, okay, as per the sequence of the processes, and assuming the output from a process becomes the inputs to the next process, or output from one stage becoming the inputs to the of the subsequent stage, and ultimately you go to the final stage. In this case, it is assembling. So, this way you represent the cause and effect diagram. So, this is referred to as process analysis. What is the run chart? The run chart is a very simple chart. The run chart is a plot of quality characteristics as a function of time. That is very important. So, here as an example you will find that these are the data you have collected, okay, the pH values of dye compound. So several such values, 20 such values you have collected, and they are plotted over these numbers over the time period. Okay, so this is the run chart for the acidity, right? So over the time period. So it's a very simple diagram. By looking at this diagram, you can get an idea about the trend in the values. So for the trend analysis, it's an important analysis in quality assessment, okay, in the quality control. So the first thing is getting an initial idea, or what you do, you plot the data over the time periods, and then you say that what type of trend it is, whether it remains constant or not, okay, around which value the other values are lying. The scattered diagrams is basically a diagram which is indicative of the relationship between the two or multiple variables. Is it okay? So here, the data of depth of cut and tool wear. If the depth of cut is more, the tool wear is more. So how do you establish the relationship? So what do you do? So different observations you take, 40 observations you have taken, and the depth is like this. If you change the depth, you will find the tool wear also changing. So you take these measurements and then you check to what extent the depth of cut is affecting the tool wear. So you plot this data. That means y-axis represents the tool wear and x-axis represents the depth of cut. So you get such type of plot, and looking at the plot, you may assume that there is a positive relationship. Is it okay? So there could be positive relationship, there could be negative relationships. That means the relationship is inverse, or there could be no relationship. If there is no relationship, you will find that almost all the points will be plotted around a straight line. Is it okay? So this is the initial observations. Now the control chart parts we will discuss in week 4 and week 5 lecture classes. Is it okay? So so these are the 7 new tools. These are the 7 new tools, and like say affinity diagram, interrelationships diagraph, T diagrams, matrix diagrams, matrix data analysis, process decision program chart, and arrow diagrams. So I will explain it in later on, but at least you should be aware of this data. That means the managers, they use a variety of tools and techniques known as the 7 management and planning tools to manage the policy deployment. This means these tools are used at the higher level. Is it okay? For quality improvement purpose, for quality the assessment purpose. So what are those? Affinity diagram, interrelationship diagram, T diagram, matrix diagram, matrix data analysis, process decision program chart, and arrow diagram. So the new 7 tools, these tools are useful in structuring unstructured ideas, making strategic plans, and organizing and controlling large and complex projects. Many companies formally integrated these tools into policy deployment activities. Okay, so later on we will be taking up examples of all these diagrams once again. So thank you so much.